Hello everyone, welcome to another lesson on linearization. So far we have defined dy dx as mere notation. We now treat dy dx as a true ratio. Given y is equal to f of x is a differentiable function, then dy dx would be equal to f prime of x, where dx is an independent variable that can be assigned a non-zero real number, and dy is their dependent variable. So we're treating the dy and the dx as variables. So let's do a bit of algebra on this. If we multiply both sides by dy dx, we end up with by dx apparently, then dy will be equal to f prime of x times dx. So the expressions dy and dx are called differentials. So when you're asked to estimate something using differentials, then that is what it means. You're using this formula dy is equal to f prime of x dx to estimate something or to solve a problem. Dy and delta y are not the same thing. Dy is measured vertically to a tangent line. The tangent line is given the name L of x. Delta y itself is measured vertically to your original function f of x. So note those. Numerically, dx and delta x will be the same, but dy and delta y will not be the same unless your original function was a line. Okay, but if it was a curve, they will be different. If it's an estimation that we're doing, we can use dy as an estimate of delta y as x changes from a to a plus delta x. All right, so a visual would probably be a little bit more helpful in explaining that. So here is your y is equal to f of x, a line in blue, and then your L of x, your linear function, is in orange right here, y equals L of x. Now your dx and your delta x is this horizontal distance along the a from a to a plus delta x, and then your vertical distance is dy is measured from this horizontal line all the way up to your L of x, and then dy by calculation is f prime of a times dx. Delta y, on the other hand, will be your difference in your function values, f of a plus dx minus f of a. Right, so it's just a difference in two function values, f of a plus dx minus your f of a. Right, so there's a difference. If the curve is higher, then your delta y will be bigger. But if your curve was lower, curve like let's see, y was equal to radical x, then your delta x would have been lower than your delta y would have been lower than your dy. So just the shape of the curve will make a difference in the dy and the delta y. Now let us use this differentials dy is equal to f prime of a times dx to solve some problems. Okay, so problem number 4 tells us y is equal to x squared plus 2x. Calculate dy and evaluate it when x is equal to 3 and dx is equal to 0.1. Now, you know dy from our formula was dy is equal to f prime of a times dx. So we want to find f prime of a. Your f prime of a is your x value. At a, your a value is equal to 3. So we have to find the f prime, or your derivative. So given that f of x is equal to x squared plus 2x, f prime of x will be equal to 2x plus 2 by your power rule. Now your x equals 3 means that a equals 3, so f prime of a will be f prime of 3. So you plug 3 in to your f prime of x function. So we had f prime of x was equal to 2x plus 3. Your f prime of 3 will be 2 times 3 plus 3, and 2 times 3, that's 6 plus 2, that would be equal to 8. Now dy by formula is dy is equal to f prime of a times dx. F prime of a was f prime of 3. We know that was equal to 8. and then dx was given to be 0.1. So we simply multiply your 8 by 0.1, and your answer is 0.8. Now what about 5 when y is equal to cosine of x? You have to calculate dy and evaluate it when x is equal to 3 and dx is equal to 0.1. So you need to find your cosine, the derivative of cosine, that's negative sine. It's going to be negative sine of x, and then times dx, which is 0.1. So that's negative sine of 3 times 0.1. Make sure that your calculator is in radians. Make sure that your calculator is in radians so that when you do sine of 3, negative sine of 3 times 0.1, you get the correct answer. So that's going to be negative 0.014 with a bunch of numbers falling, but we'll round it to negative 0.014 for your answer. So the last thing we should talk about in this section is something called measurement error. It says if the exact value of a measured quantity is a, but the measured quantity is a plus dx, then the measurement error is delta x. So when we're talking about measurement error, that is your additional part after the a, that is your dx, or delta x is the same numerical value. The resulting error is the calculated value of f of x is given by delta y is equal to f of a plus dx minus f of a. This error is known as propagated error because it's propagated from the measure in your x. It's transferred to an error in your f of x. The true relative error is given by delta y over f of a, and the percentage of the true relative error is delta y over f of a times 100. So you're making it a percentage, you multiply it by 100. What we're mostly interested in this section is our estimate from our linearized function, or our L of x, that's used to estimate the error. So the estimated relative error, so usually when you just hear relative error in this estimation section, we're talking about your estimated relative error. Even if it doesn't say the word estimated in the question, that is what we're talking about. We're using the linear function L of x to estimate what will be the function value, the function error. So we are doing an estimated relative error. And it's given by dy, so instead of delta y, we have dy over f of a. And the percentage error is given by dy over f of a times 100. Let's apply that to a couple of problems. So the first problem says, suppose a side length of a cube is measured to be 5 centimeters with an accuracy of 0.1 centimeters. Use differentials to estimate the error in the computed volume of the cube. Part B, compute the volume of the cube if the side length is 1, 4.9 centimeters, and 2, 5.1 centimeters. Compare the estimated error with the actual potential error. So here we are comparing the estimated with the actual, right? When we're told about the accuracy being 0.1, we're talking about the dx, or your error. Or so if it says accuracy of, or it says the error of, we're really talking about the same thing, or dx, as long as it's estimated. Okay, so we're going to look at how we can solve a problem like this. So our estimated error is dx. It is within plus or minus 0.1. So we can write that our dx goes from negative 0.1 to positive 0.1 included, or negative 0.1 less than or equal to dx less than or equal to 0.1. And so we want to use this to find our estimated error in the side length of the cube. Our estimated error in the side length of the cube is, remember, our volume of a cube of side length x is v is equal to x cubed. So we want to take the derivative of that, dv dx. So dv dx will be equal to d dx of x cubed. That's going to be equal to 3x squared. So then our dv dx will be equal to 3x squared dx. Okay, 3x squared dx. And then to put in terms of the actual numbers that we have for our problem, We're given that our side length was 5 and that our dx was plus or minus 0.1. So let's see what our estimated error in the volume is. We're going to plug in the 5 for x and the 0.1 for the dx. So then our estimated error in the volume would be from negative 0.1 times 3 times 5 squared, that gives you negative 7.5, to 0.1 times 3 times 5 squared, so that would be 7.5. So from negative 7.5 less than or equal to dV equals to 7.5. So that is the estimated error in the volume. So let's talk about what the actual measures are. The actual measures are 4.9 and 5.1. So then the true errors in the volume would go from the volume at 4.9 to the volume at 5.1. So the delta V would be from 4.9 cubed minus 5 cubed to 5.1 cubed minus 5 cubed. So that is your a plus delta x and minus your a cubed, right? So then these numbers simplify to give negative 7.351 less than or equal to delta V less than or equal to 7.651. So our estimates were from 7.5, negative 7.5 to 7.5, and then our real thing was from negative 7.3 to 7.6. So not too far, maybe about a 0.05 or 1.15 estimate. So the estimated error is close to the actual error in comparison. So in this case, the error in the computed volume, the estimated one is pretty close to our actual error. Let's look at one more problem in error estimation. An astronaut is using a camera to measure the radius of the Earth. The measurement is 4,000 miles with an accuracy of 80 miles. Assuming the planet is a perfect square, use differentials to estimate the relative error and the percentage error. Remember, our relative error was dy over f of a, and the percentage error was dy over f of a times 100. So let's use those ideas to find the answer to this problem. We are told that the sphere, its radius r, has an error of about plus or minus 80. That means your dr would be from negative 80 to positive 80. The volume of a sphere is 4 over 3 pi r cubed. Taking derivatives, dv dr will be equal to 4 over 3 times 3r squared. So that's going to simplify to 4 pi r squared dr. So dv will be 4 pi r squared dr. So the estimated error in the volume then would be plugging in some numbers, a negative 80 times 4 pi r squared, because of dr, so that should be 4 pi r. It's negative 80, 4 pi r squared. That's not equal to dv, that's not equal to 4 pi r squared times 80. We need a volume for a value for r, so let's just use the 4,000 that we're given right there. So plug in all of these things. We have negative 80 times 4 pi 4,000 squared over, times 4 pi 4,000 squared times 80. So the error in this case, dv over v, we need to find v. So finding v using r is equal to 4,000. That's going to be 4 pi 4,000 cubes for our v. And then just doing your division right there, we end up with dv over v going between negative 0.06 to positive 0.06. And then finally, the percentage error, you multiply that by 100, And so the percentage error will be 6%. Thank you so very much for watching. Like and subscribe. See you next lesson.